So this question 17 on the Fibonacci numbers of the integers chapter, it's leading you through some basic results about the Fibonacci sequence. So the Fibonacci sequence, of course, begins 1, 1, and thereafter each term is the sum of the previous two. And all these facts here are basically come out of using induction. So a recurrence relation defining a sequence where you have the element of the sequence defined by previous ones, that's the very essence of the induction idea, or something about this state depends on previous state. So it's a very natural approach to things about the Fibonacci, or to things about sequences defined by recurrence relations. Now, part A we proved last time. Yeah, so we were able to establish part A that the nth element of the Fibonacci sequence is definitely bounded above by 2 to the n. The second one was this part B, so that the product of, so these are two elements of the Fibonacci sequence that are two places apart, fn plus 1 and fn minus 1. We're showing that this is equal to the square of the one in the middle that they skipped over, fn, plus or minus 1. And the plus or minus 1 goes with the parity of n, because n is odd or even, you get the plus or minus 1. Okay, and that is the results. See. So go through the proof of that. So this is chapter 2, size question 17, part B. So, well, we can check that statement. We can check the base case of that statement. Okay, statement is true. Statement is true for the base case. Now, what would be the base case? Well, you see, the statement is talking about. I'll just write it up here. The result we're trying to prove: fn plus 1, fn minus 1 equal to square of fn plus and minus 1. That's the result we're proving. So I guess the base case here has to be n equals 2, because it's referring to fn minus 1. So it would have to be equal to base case n equals 2. So n equals 2 is f3 times f1. But what is f3 times f1? Well, f3 is 2, f1 is 1, so that's equal to 2. So the left-hand side is 2. Then you just have to check that the right-hand side is equal to 2 as well. Well, the right-hand side is f2 squared. So f2 by definition is equal to 1. So 1 squared plus minus 1 squared, and that of course is equal to 2 as well. So it's certainly true for the base case. The base case is true. So we can assume that the result is true. I don't think we could do this either as a strong induction or a weak induction, and I think we can do it just as weak induction, just assuming the proof of the truth of the previous case. So it's true for n equals, yeah, I'll make my assumptions like this, that it's true for n equals k minus 1, and then I'll try and establish the result for n equals k. Yeah. Okay. So I'm assuming it's true for n equals k minus 1, i.e., that would be saying that fn times, fk multiplied by fk minus 2, that this is equal to the square of fk minus 1 plus minus 1 to the k minus 1. So that's what I'm assuming. I'm allowed to use that fact in the coming argument. So now try and prove result. Try and prove the result for n equals k. See, all these induction proofs, they all take the same kind of format. Now it's an equation we have to prove, so I'm just going to do it directly. I'm going to start with the left-hand side and try and work my way to the right-hand side. So the left-hand side is f k plus 1 times f of k minus 1, and I'm going to try and work that until it looks like, put down what I think I should have. This is supposed to be equal to the square of fk plus minus 1 to the power of k. Okay, so that's the equation I'm trying to prove. And now it's looking hopeful at least. I just have to bridge these two sides of this equation. Okay. And what are the things I'm going to be using? Well, I'm going to use the assumption that's there. And I'm also going to be using the fact that this is the Fibonacci sequence as well. Okay. So, any suggestions for a first move, or a first thing to do if we're starting at the left side? If we look at the assumption we've just made, our assumption is about this quantity here. We don't immediately see any parts of that, either side of that assumption present in this expression. If we do see fk minus 1, you could argue that you could bring the minus 1 over, take the square root of both sides, then you'd have an expression for f of k minus 1 that you might substitute in for there. Then you'd be introducing square root, you'd be introducing the square root of a sum, isn't very particularly nice. So what might be better to use here is the definition of the Fibonacci sequence itself, the recurrence relation itself. So which one might I use? Well, I have to break down, you see the assumption talks about smaller numbers, k minus 2, and k minus 1. I've already got an fk minus 1 here, so maybe I should break down this first element. So I get rid of the high value of the index, k plus 1, and I replace it with k's and k minus 1s, which do feature in the assumption that I've made. So using the definition of the Fibonacci sequence, f of k plus 1 is just the sum of the previous two. That's multiplying f of k minus 1. So this is just by definition of the Fibonacci sequence. Determine the sequence is the sum of the previous two. And you can kind of see, well, we can multiply that out for a start. Fk minus 1. We're not too sure about this term, but what does look good is f of k minus 1 whole squared. So we got this product here. Okay, well, this doesn't feature down there, so we'll worry about that in a moment. But what we do have here that's quite good is the square of fk minus 1, and that's exactly what we made an assumption about. So now I can use my assumption. So instead of fk minus 1, I've got the product f of k with f of k minus 2. So, and then I have to send that minus 1 over to the other side, which would be minus 1 to the k minus 1. Remember, these minus 1 to a power. If you think about it, it's either plus or minus 1. I want to have plus minus 1 to the power k. Of course, when you look at that, you see you've got k minus 1 minus 1's here. You've got another minus there. So you actually, this can become equal to that straight away. So I can change that to a plus, and I can eliminate that minus 1. So it is already plus minus 1 to the power of k. The justification there is by the assumption above. And what have we got here? Well, okay, this isn't looking like the square of fk yet. However, there is one factor of fk there. And you can factorize that out into fk, and it's multiplying fk minus 1 plus f of k minus 2. Still got this minus 1 to the power of k. It's just algebra factorizing. And what's the final step?
Well, it's just using the original.
Using the defining equation of the Fibonacci sequence. Because here we have the sum of these two adjacent elements, fk minus 1 and fk minus 2. By definition, that's the value of f of k. So we do indeed have f of k squared. So it's just one more step there, and that's by Fibonacci definition again. So that's a proof of, so sorry, we're in the middle of the induction proof. We did the base case, we made the assumption, and we derived the next result. So we can say, therefore, by true for all n, equation is true for all n. The equation at the top of the page is true for all n bigger than or equal to 2 by induction. So the other parts C, D, and E, this is on page 30, those can be done by induction as well. Part E we did last year by induction in the number theory course, and was one of the number theory exercises. Again, can be done by induction. Check the base case is true, make the induction assumption, look at the next case, and use the Fibonacci definition in combination with the assumption. And we should get the co-primes out. And the other one too, the part C and D, which are talking about the golden ratio, the limit of the ratio of adjacent terms of the Fibonacci, because you can establish part C using induction, and then once you've got part C, you can establish the ratio Fn over Fn plus 1. Take the limit of it, and you'll see it's equal to that root 5 minus 1, 2. Is that okay? Any questions raised by that, or? Okay. Okay. Well, then we'll shoot on to the ones in chapter. Sorry, I wrote chapter 12 there. To the questions in chapter 3 on group theory. So what we'll be looking for here is to see aspects of the definition of a group being used, and so on. And also we'll be accumulating some more basic results about group theory. So as I said, in the last lecture, we looked at some of the initial consequences of the group axioms, some kind of basic facts about group theory. Some of these exercises kind of stand there as little results in their own right, kind of almost have just as much status as the ones shown in the chapter. So the numbers I picked out began with 25, 26, sorry, 25, 27, 32, etc. Have a look at 25 for a start. So 25 there you can see at the top of the page. And then 25 there. So let A and B be elements in a group G. Okay, so it's extremely general. It's not placing any conditions that the group is finite or the group is abelian or it's any particular group. So it's extremely general. It's the most general kind of situation. Just any group, 2 elements in the group. That's the first thing to recognize. What's the actual result? We're asked to prove that this expression here, A times B to the power n times A inverse, that this is equal to taking the nth power of AB A inverse for any n at z. And the proof method that immediately springs to mind is induction. An infinite set of statements indexed by the integers. It's indexed by all the integers. So this is positive n's and negative n's. So really, we'd really have to go both ways for this. We'll establish a base case, and then we can do induction upwards to get the positive integers and induction downwards. So what value of n am I thinking of for my base case then? We've got all the integers to do. What's the most natural base case? 1 or 0, which is slightly preferable. Sorry?
0.
0, yeah. 0 is the most natural thing to think of as being in the middle of the integer. And it is the dividing line between positive powers of an element, which are powers of the element, or negative powers of the element, which are powers of the inverse, by definition. So looking at chapter 3, question 25, so we'll use induction up and down. Probably need two arguments, one to go up, one to go down. So we're letting A, B be elements of a group G. I won't say G is a group, it's kind of understood in group theory unit that whenever we write capital G, we're talking about a group. But it's general, there's no other conditions. So the base case I'll look at is consider n equals 0. So that we've got this equation to do. The thing on the on the left-hand side is a b to the power 0 a inverse. What can I say about that? What is b to the power 0? 1, or maybe slightly identity. The identity of it, yeah. So if b was a number, it'd be 1. And even sometimes when people write multiplicative notation for a group, they do write the identity as the symbol 1. I'm going to avoid it. I'm just going to use E, the identity, because the danger is you confuse yourself to thinking in terms of numbers too much. But it's not wrong. So that's true just by definition of exponents group. By associativity, A inverse, it's unambiguous what it is. It's just the identity multiplying one of those. It's going to reduce it to A inverse. Strictly speaking, that's by associativity, I guess. But won't worry too much about that. And A times A inverse is, of course, equal to that. Okay, that's what the left-hand side looks like. What does the right-hand side look like? Well, the right-hand side looks like A inverse to the power 0. Is that equal to the identity? Yeah. It's certainly an element in the group, because it's a combination of elements in the group, A inverse. And you're raising it to the power 0, by definition, that's equal to the identity. That's what raising a group element to the power 0 means. It means the identity. So that's true by definition of exponents. So that's the base case. The base case is certainly true. The thing on the left at the top is equal to the expression on the right. So we can now go upwards. So assume true for some n equal to k to make this a intermediate step on the positive side of 0. We'll now try and get it which side will be? Okay, so we're assuming that a times b to the power k times a inverse is equal to ab a inverse raised to the power k. We now want to attempt to do the result for k plus 1. But it kind of makes it, so this is what we're assuming. It's easier to start on the right-hand side here. I consider AB A inverse to the power k plus 1. It's easier to make progress, I think, straight away with this, because it's easier to reduce that to the k case, because I can just split off. I've got a choice here. I can split it off on either side, but I'll split off to the left one of those. So I split off one of those brackets. I've got k the brackets left. Now I could have split that off to either side, to the left or the right. It doesn't make a difference which one you do. But now we've got our bracket to the power k. We'll just assume something about this. So we've got AB, A inverse. This is equal to A, B to K, A inverse. Now, I won't worry. I'm going to skip over all the separate associativity steps we might have needed there. Strictly speaking, I should have a pair of brackets around here and a pair of brackets around that one. And even then, there's a triple product inside it, so there should be some pair of brackets there. We can save ourselves a lot of time. We'll make use of the general principle of associativity. That whenever we have an ordered product written down, it's an unambiguous thing. It doesn't matter how you evaluate it in pairwise thing. It's always going to come to the same thing. So I'll just write down assuming general associativity. We haven't proved that, strictly speaking, in the course. I indicated on the handout that it was a kind of a important standalone result. It can be proved by induction as well. So you can see what's going to happen, of course. The A and the A inverse cancel. Then you've got a B beside a B to the K. A being identity, B to the K, A inverse. The identity essentially makes no difference. A, B to the K, A inverse. So this is A, B to the K plus 1. And that's the result we need. That's the result for n equals K plus 1. So true for all non-negative n by induction. Then you do the downwards induction. The downwards induction again is a very similar argument. Okay. Downwards induction. Meaning you assume it's true for some non-positive k, and then try and derive the truth of it for k minus 1. Then do downwards induction in a similar way. Interpreting negative powers. So if you have an x if you have an element in the group, what is x to the power minus 5, for instance? The definition of that is the inverse element of x raised to the power plus 5. So interpreting negative powers in the appropriate way. E.g. this example. So that's the definition of a negative power of group element, the positive power of the inverse element. So again, it's showing, okay, we're already starting to skip over explicitly referencing all the axioms, so there's a lot of associativity being used there, but I'm still trying to indicate the principle of the identity and the principle of inverses. Okay. Any questions about that? Okay. Question 27, I would say, is very similar. So use induction there as well. I'll skip over it for the moment to get to some of the other exercises. But if you look at question 27, it's a kind of result that feels a bit similar. So here you're saying prove the inverse of a big long product, G1 up to Gn, is the product of the inverses but in the opposite order. It's the generalization of that fact about products of two elements that you're quite familiar with, especially in the area of matrices. The inverse of a product of two matrices, the product of the inverses in the opposite order, providing the inverse matrices exist. Of course, if you're inside a group, you know there are inverses. That's what a group is. It's a thing that contains all. So you could certainly do the base case. You can even use a base case of 0 here. So it's quite funny. What's an empty product? A product of no things. Well, there's only one reasonable definition to give to it. It would be the identity element, really. Although, strictly speaking, maybe you should use a base case of 1. So you go, is G1 equal to G1 inverse? Well, yeah, it is. And then you can build up the induction from that base case. Okay. So then what was the next one in the lesson? 32. 32 is an interesting one. And it displays a nice example of a certain kind of argument. Let's read the result. It says that G is a finite group of even order. Okay, so it's not completely general. We're only talking about finite groups and only ones with an even number of elements. So it can have 0, well, the even numbers are 0, 2, first count at 0 elements, because every group has to have an identity. So you can't have an empty group. So this is a group with either 2 elements, 4 elements, 6 elements, 8 elements, any even number of elements. And, well, the conclusion is then there is an A in G, so there is a group element in G, which is not the identity, but does satisfy A squared equals the identity. So any group of even order, we can draw this conclusion about it. Somewhere in it, there must be a non-identity element floating around that satisfies this equation, A squared equals E identity. So we assume that G have finite order. Certainly E, the identity itself, satisfies this, that E squared equals E. Okay? We seek to prove the existence, I'm just basically repeating the question here, the existence of A in G such that A is not the identity, but A squared equals E. Now, on the face of it, this is a bit puzzling. It's hard to see any connection between this and the fact of the group having even order. But you can start to see a way through if you think about what's another way of interpreting or expressing this. If A squared is equal to E, there's another way we can present that fact in a nice group theoretic way. There's something special about, I mean, you can have relations like A to the power 5 as the identity and so on. But is there a way you could represent that fact, that A squared is equal to the identity, in terms of a fundamental group idea? Fundamental group ideas, we have the things mentioned in the definition: closure, existence of identity, associativity, and existence of inverses. Does that look like an inverse type statement, a statement about inverses? A multiplied by A gives you the identity. Yeah, because when you're talking about inverses, you're talking about some element multiplied by its inverse equals the identity element. And we know that inverses are unique. That is one of the initial basic facts about inverses. So just another simple equation there. Something on the left and something on the right. It's got to be related to A. Well, that equation is saying that A is its own inverse. The inverse of the element A is itself. Okay. We saw examples like this. Remember when we looked at the group of symmetries of the rectangle? So a non-square rectangle, like these bricks, it had a rotational symmetry, rotated 180 degrees about the center. That symmetry R. That symmetry satisfies R squared as the identity. You rotate the plane twice by 180 degrees, everything's back to where it started, so that's the identity. It also had symmetries which were reflection in the horizontal axis of the rectangle. Well, any reflection of the plane in a line, if you do that twice, everything's back where it started. Again, that's the identity, and it also had reflection in the vertical axis through the center. V, we call that. And again, V satisfies V squared equals the identity. So in other words, V is its own. So we can reformulate this question as asking us to show that in a group of finite even order, I don't even need the word finite. Even implies finite. Even means an integer divisible by 2. And in such a group, there must be a self-inverse element which is different to the identity. And what is the connection here with evenness of the number of elements in the group? Well, this is an example. This is a nice example of what we sometimes refer to generally as a counting argument. There's no specific definition of what that kind of is, but there's a certain collection of proofs and arguments that are quite powerful and just proceed by a careful considering of counting the elements, or maybe listing off the elements, or dealing with the elements of a set in a systematic way. You can think for our group G here. It's got a load of elements in it. One of them is special. The special group element is the identity. So one of them is particularly special as an element, the identity here. It's got a whole load of other elements, but we know there's an even number. And we're searching for one here, which is its own inverse. Now, there'll be loads of elements here, perhaps, which aren't their own inverses. So maybe there's another element G which isn't its own inverse. But that means somewhere else in the group, there must be an inverse for G. Maybe there's another element which isn't its own inverse, H. Somewhere else there'll be its inverse, H. H inverse. So if there are elements which don't satisfy this, which aren't their own inverse, really that's pointing out a pair of elements in the group. And I can keep listing these elements. Say there's a K here. Somewhere else there'll be a different element, K inverse. So we can observe elements like G, H, K, etc., which are not their own inverses. Now, when you count up all those elements, how many elements have you counted? If you look at all the elements which aren't their own inverse, you collect them all together, how many of them are there?
An odd amount.
An odd amount including the identity.
Yeah.
Yeah. So the elements I'm bringing out in the picture, there's an even number of these ones which are different to the identity, which aren't their own inverse, because they always have to come in pairs themselves and their inverse. And with the inclusion of the identity already defined, we've got, as you say, an odd number. But right at the top is the assumption that there must be an even number. So somewhere in this picture, we're forced to the conclusion that one of these dots must be an A, because there's an even number of dots in total. When we account for the identity, there's only an odd number left, and then we're accounting for pairs. If you got an odd number and you're counting them off in pairs, you're going to reach a situation where there's one left. So this poor element A, where is its inverse? If all the other elements are already accounted for, it must be its own. But this A must be the special one. There could be loads of them. There must be at least one for which it is its own inverse. So we observe elements like G, H, K, etc., which are not their own inverses and which are different to the identity. Taking all these together, I don't want to waffle too much because we've seen the essential point. Taking all these together accounts for an odd number. Odd number of elements. Because it's a load of pairs plus the identity. Meaning, because G is even, the order of G is even. You might have seen that notation, but modulus of G, well, in general, in set theory, the modulus of a set refers to the amount of elements in the set. So modulus of a set G, of a group G, will mean the amount of elements in it. So meaning, as G is even, there must exist elements like A. Like the element A shown above. This A, which is not the identity, but is self-inverse. So this kind of thing, you know, you can see it's a kind of neat idea. We haven't built the equation up out of, built the argument up out of lots of equations, or we haven't used induction. Although maybe there's kind of an inductive argument hiding here. We've just talked about it by imagining we were counting all the elements in the group, or imagining we were listing off all the elements of the group in a certain kind of way, which leads us to a certain conclusion. Okay, that's a useful thing to know. Any group of even order has to have self-inverse elements, which are not the elements. So that was question 32. We've got 45, 46, etc. So 45 is a good one to look at next. Question 45 is quite nice. Prove that the intersection of two subgroups of a group G is also a subgroup G. So to prove 45, we should let, traditionally, H would be used to denote an abstract a subgroup of a general group. So we let H1 and H2 be subgroups of G. We want to show that the intersection of these two is also a subgroup. Notice that the setting is completely general, just any group. There's no restrictions on the type of group or other properties that it has, just any group. And any two subgroups, the intersection is also subgroup. So this is quite a nice fact to know. Now, there are results in chapter 3 which speak specifically to this. Because in the subgroup section ended with two propositions, which, if you like, give us ways of testing when things are subgroups. Remember, a subgroup is a subset of the group which acts as a little group itself under the operation. So proposition 3.30 is more or less saying that definition. Subset H is a subgroup if and only if it satisfies these three conditions. These are three of the group axioms: closure, number 2, existence of identity, number 1, and 3, the existence of inverses. The one that's left out is associativity, because that's automatically true. Associativity is true for all the elements in G, but it's certainly going to be true for a subset of them. Proposition, so in some ways that's the nicest thing to think about, because it's just saying to show something's a subgroup, you just check off the necessary group axioms, establish those. That's the best way to think about it initially. Proposition 3.31 is really just a compactification of that. It just kind of, you're able to combine the closure and the existence of the identity element, those two axioms together. You kind of mush them together to get this combined one, saying that whenever you've got a pair of elements in H, product of G times the inverse of H is also in H. It just means you kind of do them both at the same time. You're doing closure and existence of identity elements both at the same time. But there's one other sneaky condition hidden in here, that also you must be sure the subset is non-empty. Now, the non-emptiness is taken care of in the previous proposition, of course, by condition 1, because it's saying that there is at least this element E in H. So that's showing that H is non-empty. So we could use either of these propositions to prove that thing. I think it's most instructive for the moment to use the first one, proposition 3.2. It kind of separates out the axiom, and we deal with each one by one. But do know that there is this kind of more compact, efficient version in 3.30. So, using proposition 3.30 then, here's the proof of this, using proposition 3.30. So we got these three conditions to check. So is the identity in the intersection? Yeah, because it's in both H1 and H2. So E is in H1 and E is in H2. Since H1 and H2 are subgroups, But that, of course, implies that E is in the intersection. Okay? Because that's what the intersection is. Set of all elements that are in both. So certainly part 1 is true. So proposition 3.31 is true. Part 2 was the closure. So to prove closure, we must take, I won't call them little h1 and little h2 as they are in the statement of the proposition, because that might confuse them with large h1 and large h2. But I'll consider a little x and a little y to be in h. Remember h, or I haven't said that, sorry, h is the intersection. Just consider them to be in the intersection. I want to prove that their product x times y is also in the intersection. Yeah. But of course, if they're in the intersection, it means x, y is in h1 and x and y are in h2. And because those are subgroups, that implies that the product xy is in h1 and the product xy is in h2, which of course implies that xy is in the intersection. So again, you see, the proving the axiom about the intersection means calling on the fact that the axiom is true in both of the sets. And therefore, you get the closure in both of the sets, and therefore the closure is still satisfied in the intersection. Okay, because the intersection is just capturing everything that is common to both the sets. So that's condition 2. So condition 2 is true from the proposition. And then we've just got the inverses one to do. And here, if we let H be any element in the intersection, so it's exactly the same kind of argument. H is in H1 and H is in H2, but that implies H inverse is in H1, so subgroup, H inverse is in H2, H1 and H2's subgroups. But then, of course, H inverse must also be in the intersection. It's in both. Okay. So this operation of subgroup intersection, it fits well, it really clicks with all the axioms. So if the axioms are true for the subgroups individually, they must also be true for the intersection of two subgroups. So condition 3 is true. So by proposition 3.30, intersection is a subgroup. Is that okay? Any questions based on that, queries? That was 45. Of course, 46 is a natural thing to think about. After we've been talking about intersections, question 46 immediately springs to mind. Is the same thing true for unions? Question 46, prove or disavow. You can see the implication here is that maybe it's not true. Prove or disprove, if H and K are two subgroups of a group G, then the union is also a subgroup. Well, first thing you can do is try and prove it. Okay. So for 46, an attempt along similar lines, an attempt to prove this in a similar way to 45, previous question, will grind to a halt. Everything falls out easily when you're talking about the intersection. When you talk about the union, you're unsure. Certainly the identity is going to be in the union. The identity is in both the sets. It's going to be in the union. But then when you look at closure, if you've got two elements in the union, all you can say, so if you got an XY in the union, all you can say is, well, X1 is in one of the two sets, and Y is in one of the two sets. You can't ever definitely locate the X and the Y in the one subgroup. If you could, then you'd know that their product is also in that subgroup. But that doesn't have to be. So if you've got two elements in the union, you could have one element coming from one set and the other element coming from the other set, and then you've nothing to tell you that the product of them is contained in either set. Okay? So the closure thing falls. The inverse axiom does go through. If the union contains an element G, G is in one of the sets, so therefore the inverse will be in that subgroup as well. So therefore, the inverse will be in the union. Okay? But it's the closure one which falls down. Closure cannot be proved. Well, it cannot be proved in such a quick, easy way as we did in question 45. Of course, that doesn't prove that it's not true. To prove it's not true, so the result looks unlikely. But to prove it's false, we need a contradiction. Counterexample. And you can find one in that basic example we looked at, which was consider the symmetries of the rectangle we looked at last time, which was the group consisting of the elements E, R, H, and E. Two subgroups are, well, we can take the identity and the reflection in the horizontal axis, and the identity and reflection in the vertical axis. Those are two subgroups. You can call that the H and the K. And H union K, which of course is E, H, and V, union. But what's the problem with this? Now, from what we said before, it seems to be the closure thing. When you multiply H times V in this group the symmetries of the rectangle, remember the group operation is composition. When you compose these two reflections, what do you get? You get R, the rotation. Okay? HV in the group is equal to R, which is not an element. So the union is not closed. So that's a counterexample that destroys this result as being like a theorem. You got two subgroups, their union is a subgroup. That's not to say it never happens. Okay, there may be cases of groups where you have looking at two different subgroups, and when you take their union, then you do have a subgroup. But it's certainly not true in general. Okay, because you cannot, this feature of closure not being respected. Okay? We know closure works within H and closure works within K, but it's when you select an element for both of them, there's nothing to guarantee that that should be closed still within. Okay, I guess we should, I've gone over a few minutes, we should leave it there. So keep working.